IEEE Energy Conversion and Conference Exposition, and he's the president of IEEE Power Electronics Society, and also he is the professor of Northeastern University, Boston. So I know you all are very eager to learn more. So without any further delay, I would like to hand over the session to our speaker. Sir, over to you.
Uh, Thank you, Narmada. It's nice to meet you. I also especially want to call out with respect and great thanks to Mr. M. Maroon and, of course, Dr. Albert Alexander. Thank you for hosting this, and thank you for inviting me. Let me share my screen. And I think I'm sharing the screen now. It might take a while. Tell me if I'm okay.
Yes, sir, it is visible.
Okay. So, um, today, with your permission, I'm going to speak a little bit about two things. One, because I'm wearing the president's role of the IEEE Power Electronics Society, I'm going to tell you a little bit more about the IEEE Power Electronics Society, although I know many of you are members. But I have a goal. My goal is to convince you that you want to be a member for your entire life. And that means that even though you're a student now and you're a member of the society, that when you're a professional, I've convinced you that it's such an exciting society that you'll want to be a member and to participate in all our activities for your entire career. And that's maybe 5 or 10 minutes in the beginning. And then the remaining 25 minutes or 30 minutes, I'll talk to you a little bit about what I see about some exciting things that are going on in the in the power electronics research and in society um, that I've noticed in different research labs. So let's begin. So first of all, propaganda. All right. First of all, um, the IEEE, of course, as you probably know, is a giant society of electrical engineers. The IEEE itself, it has more than 400,000 members, and the Power Electronics Society probably has about 14,000 members in it. So we're one of the societies within the IEEE. There are about 40 societies in IEEE, each of different specializations, and ours is the field of renewable energy and power electronics. What we want to do is be the global resource for all your needs in sharing knowledge and in networking in the power electronics field. And the way we do that is we try to foster power electronics technology for innovation and benefit for the benefit of humanity. So we do that through technology, through innovation, and through education. And we're doing it for the benefit of society. Sometimes I just like to mention it that power electronics can have high impact and that we are in a field that is quite important because we can benefit society. If we look at what has gone on and recently with some of the major advancements in the field of technology that have brought so much quality of living to other people, we looked at power electronics has been an integral part of that role. And we'll talk a little bit about that today. But just to say renewable energy, electric vehicles, all for clean energy. Even when you talk about this just AI revolution, the artificial intelligence revolution, that has to be powered. And that has led to such incredibly new, sophisticated power electronic devices because it takes massive computing to do machine learning, and we're driving it behind the scenes. Oh, I forgot to mention, because you're on this ceremony, this seminar today, if you are not a PELS member right now, but an IEEE member, we have a code that should work. Sometimes they work some days, and sometimes I don't know, they seem not to work. But you can write this code down. This is if you've never joined the Power Electronics Society and you want to try it for the first time, but you're already an IEEE member. I do not have the ability to offer free membership to IEEE. I only can say that if you haven't tried us and you're already an IEEE member, put this code in and sign up for on PELS under essential membership. Okay. So What is the IEEE Power Electronics Society and what is our purpose? I think what we're trying to do is support you, the people that want to pursue careers in power electronics, and to provide great support for you throughout your entire career. I mean, we're member volunteer centered. Now, when I was graduating, which was, say, an undergraduate in the early 1980s, um, we tended to work for one company, maybe two companies. It was you got hired by a giant company and you stayed in the same technical area. I mean, occasionally you might move to upper level management, and but you in general it was a slow and steady approach. And I don't know if you remember the tortoise and the hare, the Aesop's fable, where the tortoise is racing the rabbit, the turtle's racing the rabbit. And I thought that when I think of that reflection of the Aesop's fable, that's how IEEE and the Power Electronics Society, maybe that's how they started and they should be. Now, the Power Electronics Society, this is PELS Day, it was born in 1987. So IEEE was established, I would say 70 years prior to that, 80 years prior to that. So it had this infrastructure of creating a professional society for members that were going to work in the same field generally and in the same one or two companies throughout their career. But we need to adapt, and the Power Electronics Society has been leading the way in adapting your career support if you become a member, because we know that nowadays, oops, yeah, nowadays the you're more like the rabbit. Okay? That you're probably going to work for multiple companies and you're going to go fast paced. You might go and start at a startup company in your field, but then again, you might switch to a bigger company later, a new company. You might switch technical areas. You might go to now, because we're so interdisciplinary, materials even. You might go to system. You might go to management. And this is the typical approach now of somebody who's starting the career. And I would say neither is better. Some of you may end up and work for a company steady, like a big company like ABB or Siemens for a long time, or some of the car companies. But no matter what, whether you're taking that rabbit approach or that turtle approach, the IEEE Power Electronics Society tries to create programs that throughout your career you can have mentoring, you can have training and networking so that you can survive and also excel in the field of power electronics. So how do we do that? Well, we're volunteer driven, just like Mr. Arun and Dr. Alexander today. We run many, run many local chapters and seminars. You have access, if you participate in these chapters, to distinguished lecturers. In our distinguished lecture program, you can apply for them and get funding to have world famous researchers come and visit. They can be at the regional level, so they don't have to travel so far. Um, so we have a lot of other activities that we can do at the conference levels, like some of you know. One thing I want to make your chapter aware of is we have very strong in developing women in engineering programs. And I would encourage your chapter to contact the Women in Engineering program, and you can do this at the student chapter and get more funding and run a Women in Engineering event where we can bring in panel discussions about biases, about inspiring stories, about how people achieve great things in their career. And it's a separate funding that we can give you if you decide to do a Women in Engineering event. We have mentorship programs, young professional programs. So even though, for example, you get the normal chapter money, we have other money as supplements that you might consider to apply for. But one thing that's pretty interesting is we're volunteer driven. So like today, you ran this workshop today in honor of PELS Day. Likewise, you would do the same for if you want to do a conference or a special panel, and we would be willing to support it. But you provide, it's like you pay to volunteer. But when you're volunteering, you're networking with people. So it's really a very interesting thing. But some other membership benefits include conferences and workshops. I think many of you know um, we have Intellect. It's one of our conferences in the IEEE Power Electronics Society. It will be in India in August. And I think I just noticed that they opened up a late breaking research paper submission that you might be able to apply to. So you can still even submit, even though it's in August, you can submit a two-page paper to it if you have some research. And we're trying to have more conferences in India. So besides Intellect next year, this year in a few months in India, uh, it's in Bangalore. Next year, we're going to hold one of our flagship Asian conference, IEEE ECCE, will be in India. So we're just trying to expand our global outreach to different locations. And I hope you can participate. Of course, many of you know our flagship publications. The magazine is one of the best magazines in the electrical engineering field. When you're a member, you get a free copy of the IEEE Power Electronics magazine. The flagship research journal, the IEEE Transaction on Power Electronics, has become the most downloaded electrical engineering journal of all throughout the world. We have other journals, the IEEE Journal of Emerging and Selected Topics in Power Electronics, Electrification Magazine, the Open Journal, Open Access Journal in Power Electronics as well. One thing that we did, I think it was last year, it could have been this year, is that we understand that sometimes in some countries it's difficult to pay the overlength page charges in some of these transactions. So, because of financial resources, and we extended in this case the overlength, the number of pages that a paper could be before you pay the overlength page charges. So we went up from 8 to 10 pages for free. And so you could submit a paper to the IEEE Transactions on Power Electronics. And if it's under 10 or less pages, there's no charge for the page charges. Now, of course, this is one of the more difficult journals to get admitted to publish a paper, but we're just trying to make it more accessible. I do think that one of the best things you can do as a member of the Power Electronics Society is to join a technical committee. What we do in the Power Electronics Society is we divide our fields into 12 technical committees. So no matter what your research interests are or your career interests are, technology interests, you can find a technical committee of about 300 people in each one of these technical committees that have a similar interest. And therefore, you can join a cohort of people that have the same interests as you. They discuss the same topics. They want to network with other people who have the same fields. They want to put on workshops and seminars. So I would suggest that when you do that, your networking becomes immediately global. When you start to participate, join, and volunteer, then you're interacting with people with the exact same research interests. And I'd also tell you that when I did that about 30 or 40 years ago, when I was straight out of school, I met people, young professionals similar to my interests, and we become friends for life. And when that happens, the Power Electronics Society um, becomes not just a professional society, but sort of a social society as well. I mean, I love it when I go to workshops or every 2 or 3 years, I see my good friends there. Um, in person. And then likewise today, as you saw, I saw good friends on the Zoom meeting. So it becomes just part of who you are. And it's why when I joined the IEEE Power Electronics Society, I became so excited about it. And it became such a part of me because my friends were in it and we did so much together that I'm dedicated to be a member for life. Okay, so that's it. So how you join the technical committee, I'd go to the IEEE PELS web pages and click on technical and find the link and just sign up for a technical committee. Now, with your permission, what I'd like to do is for maybe 25 minutes, talk to 20 minutes, talk to you about where I think power electronics is going in the future. And I don't think you need to be an expert in power electronics to just get a feeling for what's going on. I try to keep it at more of a high level, although please feel free to ask me any technical questions. Um, let's look at what's going on in power electronics. It used to be, and now this isn't just power electronics, this is the grid. This is different than what it used to be. It used to we have one coal fire plant, and then power might be over here by some electrical generating plant, and then it's just all the energy is sent in one direction. What we can see, first of all, is we have different types of generations. We've got power stations, we've got renewable turbines, you've got solar photovoltaics. Please understand that the power stations are creating usually 60 hertz from fixed grid frequency at high power. Photovoltaics are creating DC. Okay? Combined heat plants now have not only heat energy, but they've got electric energy. So it's a combined types of energy. You've got battery and energy storage. Okay? And when we look at this, what we see not only are different types of generation, but we are seeing different types of loads. I mean, you look at now down at electrical here, you've got the computers and the power supplies, I guess the automation, motor drives, batteries are now, well, you can think of batteries, they're not only an energy source, but they're a load because we have to now recharge them. And now we're talking about electric vehicles, plug-in hybrids, right? And when we do that, I'll talk in a second. Usually we think about charging the electric vehicle, so that's a load. But there's no reason why we can't send the energy back to the grid, maybe for peak shaving. Okay? So times have changed. Now, why can we put this all together into one system? I'm going to tell you that the reason is our power electronics. If it wasn't for the power electronics, then you could not integrate all these different types of loads and these different types of renewable energies. Power electronics is sort of the glue that's making all this happen. So let's talk in particular about what's new. You know, power electronics really it's not a super old field. There was spacecraft electronics in the late 60s and 1970s, but that maybe was slow switching frequency, and they were just starting to use BJTs, you know, in space in sending satellites. Then the 80s, the MOSFET came, still on silicon, and it didn't really take off, you know, a huge amount until the power MOSFET, which we call the synchronous rectifier, maybe started to be designed and developed and then commercialized. And that really was the late 90s. So when you think about it, it's the if that started to just magnify the career and make everything happen, we're looking at something that, 30 years where we're starting to see a renaissance of power electronics. And as you can see here, when we designed and power electronics was first started, you basically were saying you have a power source and you want to send that power source, convert it to the right form of electricity, the right voltage, and send it to the load. But we have different things now. We have this batteries. And for batteries, not only do you have converters that need to charge the batteries, whether they're in the electric vehicles or they're just energy storage or they're in your cell phone. Okay. So that's charging. But likewise, if we're talking about grid or microgrid, though that same converter, we would like to go in the other direction. You'd like to go from the DC voltage of the battery and send it to the grid. Or you would like to be able to go from the AC voltage from the grid and set it to the battery. You could have separate converters that do that, but why not make it a single converter with bidirectional power flow? And I would say that's one of several big ideas that has sort of changed the development in power electronics recently. Okay, now, many of you are used to the grid. And you have these huge distribution stations, big transformers, and likewise you have giant breakers and overcurrent protection devices. But now we have the ability to change that. Why do we need these transformers at 60 hertz that can take up the size of like 3 classrooms, giant classrooms. If you ever seen these distribution stations, why are we doing that when we have the ability to convert those AC, that low frequency AC, switch it really fast, reduce the size of the magnetics because you've changed it to high switching frequencies. And while you're doing that with power converter devices, add in software and in hardware really small protections, and we call that solid state circuit breakers. But when you're doing it at high frequency, the magnetics can go down 1,000 times the size and volume. So, do we think of a future that we're going to start to eliminate these giant breakers and these giant 60 hertz in the United States, 50 hertz in other areas, transformers? There's no need for it. Another thing we can think about is ask the question, why are we doing some of this? Look at what we're doing. We're sending alternating current in the United States, 120 volts. Really, we send 240 volts into the home. It's three phase, maybe 408 volts. And we send it into the home. Then what do we do to it? Well, we rectify it, step it down, right? Um, and then no matter what the load is, our loads are looking and are working almost solely on DC power. So why are we doing a lot of this 60 hertz conversion with transformers? Maybe what we should be doing is when we get to a big office park or something, is just convert to a higher voltage DC, 600 volts, 1,000 volts, and send the DC volts inside the buildings so that we don't have to use like 120 volts and then lose power when we have to rectify it, AC to DC, and then another DC to DC. So maybe we're looking at a future at some voltage levels where in the buildings we're going to have DC buses. And then the question that everybody's always asking is, what about artificial intelligence and power electronics? And I would say that's also driving the future. So, for maybe 3 or 4 minutes, let me talk about each one of those 4 devices and we can open up to questions. Bidirectional switching. Now, first of all, if we're going to do bidirectional power flow, for years we've been trying to have a bidirectional switch. I don't know what your experience is with this, but if you look here, this traditionally is how we would do bidirectional power flow. Some of you, this might be a complicated topology, but what I'm showing you here are back-to-back MOSFETs in series, and they're operating so that the inherent um, body diode um, are in opposite directions. So basically, if this is the drain on top switch and that's the source, then you would connect source to source here, okay? And then that's the drain. So what happens is when both switches are off, the diodes block current in either direction. You see that? The diodes, if the switches are not conducting, the diodes are blocking the current in either direction. So you have bidirectional blocking. And when both switches are on, then you would have a low resistance path so that the switches that your current can be conducted in either direction. So this is how we build bidirectional switches right now. One way to do it. But they require separate devices, us to have different gate drivers, and then likewise they have 2 separate switches. So you're actually building here, this is 2 separate switches, and you have a lot of switches. Uh, and this is the way that's traditional to do it. The, for years and years, I think for 25 years, people have said, well, just wait for the bidirectional switch. We're going to have build one device, one package in which you can put a signal gate drive in, and it will be able to do bidirectional blocking and bidirectional conduction. And for 25 years, they've been promising it. But now I would say that I have finally seen something that is ready to go to the market. It's not in production now, but it's basically ready. And that's I just took with permission from ETH Zurich. I took one of their devices, and they have competitors. and they're probably beginning to market it. I would say in the next years, what they've done is basically they're combining the drift regions. So you do have, it sort of looks like you have two switches, two MOSFETs, um, but they're all in the same, in the monolithic, in the same silicon and the same silicon substrate. So you can apply a single gate, and they're sharing the drift regions. Okay? And so because of that, what they've discovered is that they can get 4 times reduction in chip area for the same resistance that you would have in conduction. So I'd say that one big thing that's arriving is a bidirectional switch. And I would say finally, it's kind of got me excited. Okay. Sorry. I see. Yeah. Here's a picture of it. They've got bidirectional switches and they've got experimental plots. Um, and it's pretty exciting for people like us in the field. Okay. So that's number one. Like I said, I'm very briefly going to talk to you about each one of these and then just sort of open up in questions. I've got more slides if you want to know technical details. Let's talk about eliminating the 60 hertz giant distribution transformer. So often what we have is a giant 60 hertz transformer. Then it's giant because you're switching at 60 hertz. What is preventing us now that we have such high power switches and great low switching resistance devices? What's preventing us from building a solid state transformer? That is, what we can do is here at the distribution level, 3 kilovolts, 3.6 kilovolts AC. Okay, we send it to a rectifier. So now we have DC, maybe at a 6 kilovolts here. Now we can put it through a dual active bridge, half bridge converter here. So now, but this is at high switching frequencies. So this is a DC to DC converter. Step it down to a lower voltage and then send it to an inverter. Okay. So what is the purpose of this? This can be what we call a solid state transformer, an AC to AC converter, right? We took 60 hertz. Okay. Didn't have to be the same frequency, but it could be any frequency. And we converted to another 60 hertz output in the United States. But this could have been any frequency, and so could this, because we separated the inverter operation from the line operation. But because we've done this, if we rectify first, you can switch at a very high switching frequency. Now we're looking at some of the high silicon carbide devices that can handle higher switching frequencies at high power. Okay. Sometimes what I've drawn here is an AC to DC converter, a DC to DC converter, and a DC to AC converter. So now we can start thinking about combining them and minimizing parts as well. These can be high power semiconductor devices. And when we do this, what we've demonstrated in the power electronics field is that through software now, you can include the overcurrent protection, right? So if you have a short, you can just open everything up and you do get the protection. And so we can combine this with a circuit breaker and it can be made very small. But likewise, we're doing it instead of at 60 hertz, we're doing it at tens of kilohertz at high power. I mean, at lower power, you could do it in the hundreds of kilohertz. And the size can be about 100 times smaller in volume reduction. So we can start to put things like this on electric ships, in which space is very important, right? Okay. Now, one way to do this, like I said, is with combining these solid state transformers and start to combine parts. I just wanted to tell you that this is what we've done at Northeastern University. We call this a universal converter, and it has the properties of a solid state transformer, but a little bit special. Before I was telling you that you took AC line in, could be three-phase AC, and you converted it to AC on the output. we see a need that maybe in electric vehicles, for example, or renewable energies, you might want something that's universal. That is, the input can be anything. It can be DC, it can be single phase AC or three phase AC. Doesn't matter what's on the input. And then the output should be also DC, or if you prefer, single phase AC or three phase AC. So you can see why we use the word universal. But we also start to combine parts. And if you notice, got very few components here. Um, and this is the isolated version, and this is the non-isolated version of one of the topologies. Northeastern University does this. Um, we have, of course, there are other groups that are doing these universal type of converters. Georgia Tech focuses on, instead of, we call this a Chook-derived based universal converter, they do a dual active bridge um, converter. But no matter what, the benefit is that it's universal. Okay? It doesn't just limit itself. So you can start to think about in electric vehicles, you can have onboard charging that can go from either single phase AC to three phase AC and convert it to DC, or you could use the same device and start to power your alternators or drive your motors. Okay. So therefore your electric motors, right? So you have the ability that one power converter can do it all in universal, including all the solid states circuit protection, so eliminating the circuit breaker. All right, so that's another field that has sort of emerged. What I've always thought amazing was I don't know anything about these if how accurate some of these predictions are, but if you look at the prediction in 2020, these solid state transformer markets, they said it was about 140 million. They're predicting 438 billion US dollars in a few years. I mean, I always think that this is never true. That this, but this does. These numbers are crazy. That's just an incredible market growth. I do think though it's a hot field. I don't know if it's that hot. Okay, that's two of the exciting fields. Let's look at this other thing, and that it's kind of maybe early, and people have been sort of wondering if it's going to take off. There's this Open DC Alliance. You'd be very interested in it. There's a couple of alliances. This is Open DC. You can check it out on the web. It's where 58 companies are participating with the idea that we can start to distribute at medium voltages. They haven't decided what voltage, but maybe it'd be 1,000 volts. Distribute DC because we have the ability now. If we think about why are we distributing AC, it was the Tesla versus Edison debate. And, AC won because they had no ability to transmit DC at a high voltage back then because they couldn't create it. But we do have the ability now with DC to DC converters and the ability to stack converters, cascaded multi-level converters, so that we can create DC converters at very high voltage that share voltage stresses so that we can use normal size switches and efficiently transmit. Now you have a higher voltage DC and transmit it distances. If you want to transit for it to go tens or 100 kilometers, then you probably want 100,000 volts DC. But if you want it just to be, like 500 meters, maybe 1,000 volts DC is good enough for the power loss. And so you're eliminating a lot of the AC to DC converter losses and the power factor correction issues because you can have one big power factor correction circuit. So companies are wondering if that's true. And if that happens, you're going to start to see a lot of new products that are going to be trying to take whatever this DC voltage is, let's call it now 800 volts, okay, maybe into the building, and you want to go 800 volts now to 1 volt in a data center, right? From DC to DC. Uh, Industry and commercial, you might have DC loads here that need 48 volts. So you're going 800 volts to 48 volts. And that, if it takes off, is going to define a whole bunch of new products that might evolve. So I'd keep my mind out and be thinking about problems about high step down and actually, if it's bidirectional, high step up converters now, if we're starting to talk about higher voltage DC buses. Okay. And finally, I'm sure everybody's always wondering, what is the benefit of artificial intelligence in in power electronics. So I think that is going to influence us in multiple different ways. Um, First of all, in control, of course, and fault monitoring and fault detection. Uh, the one thing that we say is that real-time control might not need advanced artificial intelligence unless it's a very complicated system. That is my opinion. It is not a fact. But we can often, in our power converters themselves, at the design level and at the board level, we can use really low-cost microcontrollers, and those converters and their controllers are really fast and they're well designed. So maybe we don't need it as much for real-time control. Let me at least say that we haven't discovered an application in control yet that is that one idea that is showing a benefit to artificial intelligence that we can't do really at a little bit lower cost and just as well with a microcontroller. But we do know that as we're collecting data, that fault detection especially at the big system level can benefit from all the data analysis that machine learning can give. And maybe from that and the data analysis, we can start to get maybe precursors uh, beforehand that can predict that certain power converters are about to fail and maybe tell us where they might be starting to fail. So that's sort of condition monitoring. And that's been known that machine learning can do that for us for a long time. But the problem is we don't have much data because it's so competitive that companies on power converters at the board level are not sharing data. Now, what I think is a little bit more exciting is at the design level. Again, my opinion, it's not what people might argue, is that we might be able to do things new with machine learning that we couldn't do before because um, we might be able to design magnetics or board layout in shapes that are different than before with different design criteria. Because right now, what we're doing is we're buying commercial off the shelf prices. We're thinking in like two-dimensional planes. Suppose we had unique spaces like the corner of an electric vehicle. Maybe with machine learning, we could redesign the magnetics and the switches in such a way that it fits in the strange geometry and even has better performance. So we do see some of that. One of the things, for example, is that we can ask is if we look at most of the papers in the field of machine learning for power electronics, just through keyword search, they're usually in real-time control. And as I was saying, that some of those papers, maybe it's not necessary to do it. So, for example, just a typical paper is that they needed to sense data up to a megahertz, and so when you do that, we know how to sense the voltage and current data, but to do it at that high sensing speed, you can't use like the cheaper microcontrollers. You might need an FPGA. So you have to ask yourself, is it worth it? Especially, when we think about what it is that is limiting the power electronics field right now. And so um, applications to machine learning and power electronics really has not skyrocketed a new field for us yet. Maybe when we're talking about an entire system, like electric vehicles, then we can start to look at the reliability and get the data. But the problem is right now is data is not being shared. This is a field, an issue that has happened in other areas like the healthcare industries that they overcame. That the healthcare industry and the hospitals and the companies figured out a way how to share data of all the failures. In that case, it was illnesses by anonymizing the data in a way and putting them in neutral sites so that researchers could develop machine learning algorithms for better treatments in the medical field. So likewise, I would say that maybe the future for us is that we need to have some shared resources like that. Of course, what people are talking about now is a digital twin. That's the idea that you can take a complicated system. Here, there was just a paper for a buck converter and just measure the voltage and current and then from that, create this data model that would behave just like that original system. This what paper was just an example of how you would do it, because you would never do it for such a simple thing like a buck converter. But maybe we have a complicated electric ship in which we get enough data on it with a lot of voltages and currents everywhere, and then we can create with enough data a model, a very precise model of that entire electric ship propulsion system. But right now in our field, it seems we're a bit more stuck in just like data models or these digital twins for systems that we already have good models for. And I'd suggest that until we actually have a system that we can't model otherwise, artificial intelligence is really not going to take off. All right, my last application of artificial intelligence was this magnet. I don't know if you know, we had a machine learning contest in the IEEE Power Electronics Society. And the idea was that if you know the field, how do you measure the loss? How do you predict the losses in inductors and in transformers? And we've been using this old Steinmetz equation since 1890. The thing was, Steinmetz equation was a curve fit, simple equation um, based on AC input and a certain shape of geometry of a core, a toroid core, I think, okay, and a certain material. And we know that now we have DC to DC converters, that Steinmetz equations got full of errors. So we had this contest last year in which we asked, can you build machine learning models for more accurate DC to DC converter magnetics? And so that's just sort of an area that I'm pretty excited about. But if you ask me what I think is eventually going to happen, that's soon to come, I don't know about soon, but suppose we had an AI tool for automated PCB design, part selections, circuit diagrams, and it was all comprehensive. I think maybe that's the big thing. So maybe what would happen is I put in a command, design a power converter, gave it the site, height and width specifications, the volume. It had to have a certain efficiency and tell it the input voltage range and its power range, and then have a conversation with it. But the goal is that it would provide the circuit diagram, the Gerber files, the bill of materials, and do it all together for you. Now, it might not be able to do this, right? It might not be possible, and it would respond and say, oh, no, this is too hard because of these reasons. Are you sure you can't allow us a larger, height on our magnetics? Because if we do it this way, we need multiple magnetics and we have to parallel and we can't fit it into the board space. So I can see that sort of maybe in 5 or 10 years coming. I promise you that those design companies are working on it. Oracle, OrCAD, all these companies are trying to figure out how they can improve their design in doing this. But I think that's sort of what I would say is the future of machine learning. All right. So with that, let me go to my final slide and just say that I've talked just a few of the exciting things on it, but I didn't talk about everything. Okay. Some of you have heard of this idea of grid forming inverters, in which you have an inverter in which you don't need the grid. They can combine why we might combine 100 PV inverters so that it behaves like a coal-fired 100 megawatt grid. Okay, so why do you need the grid? Especially, right now you need the grid signal to operate your inverter. Suppose there is no coal-fired generator, synchronous generator. Can we just use all the renewable energies in different locations to form a grid? And that's a hot topic called grid forming inverters. Um, Active power filters, things that we can do, differential power processing, many, many more areas. I think all these are other research areas that are really hot and emerging in the field. But with that, I only could talk about a few of them. And so with that, I'll just stop. And then Narmada,
Thank
I
you,
thought
sir.
maybe you could open up with some, yeah,
Yes, sir. It was really a wonderful presentation.
thank
Shall we
you.
go with query session, sir?
Yes.
Yes, sir. Participants, if you have any queries, kindly post your queries in the chat box, or else you can unmute yourself and ask your queries.
So do you read the question or how do you want to do this?
Yes, sir. I will read the question, sir. What skills and knowledge will be crucial for engineers entering the field of future power electronics, sir?
Right. So let me start and tell you that it was much easier when I was your age. I don't mean to discourage anybody, it's pretty exciting. But when I was your age, power electronics, you just needed to know electronics and control. Okay. Now, I'm sorry, I'm going to list them out for you. You want to know what skills? I think you should know some computer engineering, how to program microprocessors. Everything is digital now. Okay, that's number one. A little bit of material science is helpful. Now, you don't need to. I don't have a great material science background, um, but semiconductor physics is quite helpful because we're talking about silicon carbide and gallium nitride now. You really don't need so much of it, but the basics of it is helpful because you drive the gates differently with them, and it's nice to know why. I also love controls because of the microgrids. And then I have to be honest, machine learning. So I think that's going to influence the whole systems. Okay. So I have just named so many fields. You need to be a computer engineer, you need to be a systems engineer, electronics, and sure, why not know a little bit about power systems? Okay. Those are the hard skills. Hard skills in the United States means the courses. Courses. Okay. Can I give you the standard response for every electrical engineer? Um, since we're just among friends, and I'll whisper it to all of you, okay? I don't think writing is as important as PowerPoint presentations anymore. I know that everybody will say communication, you got to be able to write reports. Nowadays, if you have PowerPoint skills, little animation, even when you talk about, I know students, they know how to use machine learning to make the most amazing PowerPoint slides. I think that'll get you really a little bit an edge above other people.
Thank you so much, sir. Participants, any other queries?
Sir, I have a question for you. How you are managing your IEEE skills as well as your academic skills? How parallelly you are taking both?
Oh, well, so now we can talk philosophy. As Dr. Alexander will know, we talked when we were in Boston often about life balance and everything. Okay. So, first of all, it's nice to have a mentor like Dr. Alexander. For those of you who don't know him, he has a wonderful demeanor and pleasant and enjoys life. How about this? I have a saying that I try to live by: do what you love and call it work. Okay, I love it. All right. And that's the thing about the Power Electronics Society. I don't think it's work. So if I'm doing my president stuff, I'm with friends and we're socializing at the same time as doing things and advancing something that I believe is clean energy. When I'm with students, I'm enjoying the interaction. It's not, for me, it's not me lecturing and teaching a class. It's interaction with the students and enjoying the benefits and engaging their career. So it's what I love. So when I do that, it doesn't wear me at all. What wears me a little is traveling, which I don't like to do so much. So that's why I'm doing this by Zoom. But
Thank
that,
you.
do what you love and call it work.
Thank you, sir. We got an another query from Jyotika. What are the emerging career opportunities in the field of power electronics, sir? This is her query.
Yeah. So I just want to be clear that what has been an amazing realization to me is that in the United States, power electronics students never have had ever a trouble finding a job. I'm sorry if it's not true in India, so I have to speak through my window, and let me explain. The same things that I mentioned that scares you about power electronics is that you want to know computer engineering basics, you want to know systems, you want to be able to design circuitry and a little bit of machine learning, mean that you have such a broad skill set that you can get hired by so many different types of companies. And what has occurred is that in recent years, in the last 10 years, is every company needs somebody with a skill set that understands how to make their products or simulate products to be of higher power efficiency. You can't ignore it anymore. This means that it's not really renewable energy companies only that are doing it, or car companies, or power supply companies, or Infineon, right? You know, the switch companies that are hiring. It's all the consumer electronic companies and consumer product companies are hiring power electronics engineers. So my students get hired. I mean, I could go just recently. You know these I don't know, these watches that people wear that give blood pressure and, you know, oxygen content. It's a big thing. They're hiring a huge number of power electronics students. I have students that are getting hired from in the audio industry because the speakers have to have students that can design the circuitry and the amplifiers, along with the traditional companies. So the thing is, when one market is not doing well, the other markets are hiring. And so students, even in the times of bad economy, students were always getting a job. So what makes it really difficult about power electronics is you have to know so many different multidisciplinary fields. That makes you so marketable.
Thank you, sir. We got an another query from CLI.
Shreya, ma'am, our past chairman of IEEE Power Electronic Society Madras section. Welcome, ma'am.
Yes, sir. Yes. Thank you, sir.
What is the scope of reliability analysis research for power electronics?
Great question, because there are two real areas that people are working heavily on. One is at the component level. New materials have emerged in power electronics. So gallium nitride and silicon carbide are beginning to replace the silicon switches. Because of that, all the main switch companies are looking at trying to find, first of all, what are the precursors to those switch failures? What's the best way to test them and to drive them? And then sort of like, especially at the thermal level, to do thermal analysis and relate that to reliability. So that's a big area in the semiconductor switch area. But at the system level, we're starting to see that power converters are going into bigger systems. And so from that, it's at the systems level, and that's at the machine learning level, I think, reliability. Although you can do it without machine learning. But more modernly, it's going to be people are applying a lot of data. So that's at the EV level, or you might get hired in an aviation company that's looking at it in the electric aircraft level or the electric ship level. I say electric aircraft, electric ship. All these companies are going more electric. They could be hybrid. So that's at the higher system level. So it's at two different levels.
Thank you, Professor.
Thank you so much, sir. I think so everyone are clear with your session, sir. Thank you so much, sir. Now I would like to call Dr. Albert Alexander, sir, for the token of gratitude.
Okay, so thank you so much, sir, for spending your time in delivering the talk to the IEEE Madras section. As you all know that, in India, we are having very many institutes. We are having our IEEE Power Electronics chapters. We are keep on renovating the membership drive for the IEEE Power Electronics. And thank you so much. Under your leadership, we'll be rock this Power Electronics as one of the notable society under our IEEE section. And three things I want to say about my professor. Okay, what the people does not know about Professor Brad Lehman. Many people knows that he's a professor of Northeastern University and also the past editor of IEEE Transactional Power Electronics and present president of IEEE Power Electronics. The unknown fact is he served as a head swimming coach and diving coach. So he's a very good sports person. And second one is he's also served as a consultant for a design of the Olympic pool in Atlanta in 1996. Okay, so this gives an overview that everybody can excel in academics, research, and also in sports. Okay, so he also gives insight about the sports. And the third one thing is, and also for all the participants, the one thing what I admire from my professor is, every week he will cook the food and he will take the food in his vehicle, and on the way, whoever the people he meets the needy one, he will deliver the food to them. Okay, so even that we are following. I am following over here. The same thing we also should follow the notable quantities what my professor is doing. That is, he cook by himself and take the food, and on the way, whoever he meets the needy, he will give the food along with one water bottle, and he will go off. Okay, so such an amazing person, and we are very honored and humbled and very grateful for his notable presence. Thank you so much, Professor. Thank you so much.
It's my honor to be here with you, Albert.
Thank you.
Thank you, sir.
Narmada?
Yes, sir. I thank our today's speaker, Dr. Brad Lehman, sir, for spending his valuable time in giving us the most informative session. Your expertise in power electronics is truly an inspiring one, sir. Thank you so much for your inspiration. We will surely have this in our mind for future purposes, sir. Also, I would like to extend my sincere thanks to Dr. Albert Alexander, sir, Chairman of IEEE PELS Madras Chapter, and Mr. M. Arun, sir, Chairman of IEEE Young Professionals Madras Section, and Dr. K. Porkurman, sir, Chairman of IEEE Madras Section, for providing us the golden opportunity for organizing this event. So last but not least, I would like to thank all the participants here. So thank you so much for your participation. Thank you, guys. Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. If you have opportunity to visit India, please do come. We are always happy to host you at IEEE Madras section. Thank you for joining with us.
Okay. Have a great summer.
Thank you, sir.
Thank you, sir. Thank you, guys.
Thank you, sir.
Narmada, you can post the feedback link in the chat box. Participants are requested to fill the feedback form. Thank you once again for joining with us.